Hi there. When we first discussed temperature, we said that temperature was a measure of the kinetic energy of an object. We're not going to look at that in terms of ideal gases. The motion of a gas is described as this random motion where gas particles are moving around, colliding with one another in the walls of their container. That's how we came up with the idea of pressure. The motion of these particles clearly is a form of kinetic energy. What we're going to look at right now is how we relate the idea of kinetic energy and temperature. The equation we're going to look at is the relationship between kinetic energy and temperature, which also contains a constant. To complete this relationship, we have to put in 3/2 K. I don't want to go into where the 3/2 come from. You can look it up in your book. It's interesting, but it's not important for the practical discussion we're going to have right now. K is a constant known as Boltzmann's constant. And the value of Boltzmann's constant is 1.38 times 10 to the negative 23 joules per Kelvin. This is actually the kinetic energy of a single particle or a single molecule. To use this in conjunction with other formulas we know, it really comes down to substituting what we know as the kinetic energy from our mechanics unit of 1/2 mv squared. So if you knew the mass of that molecule and you knew its temperature, you could solve for its speed. Or vice versa. If you knew its speed and its mass, you could solve for its temperature. If you knew the temperature and the speed, you could solve for its mass. So putting those two things together and creating a hybrid called 1/2 mv squared equals 3/2 kt can be very useful. Now let's be clear, the formulas that we looked at up in this section are for a single molecule, and if we want to talk about a group of molecules, so a volume of a gas, what we have to do is make a slight change here. The energy contained in a group of molecules still has this 3/2 in it, but it depends on the number of moles, R, the same value used in the ideal gas law, and the temperature. So this is for a volume of gas. And often this is actually also referred to as the internal energy of the volume of gas. And this also can be used in conjunction with some of our other formulas. So what I'd like to do is an example. This is supposed to be a cylinder of gas. We'll have some gas particles in here. The cylinder contains 2 moles of gas and is at a temperature of 20 degrees Celsius. The gas that we're talking about is helium. Now the first question is, what is the internal energy of this gas? The internal energy, if you recall from the previous page, is equal to 3/2 nRT. And we have all the information we need to do this, except for we have a couple issues. First of all, the temperature is supposed to be in Kelvin. So if you recall, to get from Celsius to Kelvin, we have to add 273 to it. So this is going to bring us up to 293 Kelvin. And also, if you recall, the value for R is 8.31 joules per mole Kelvin. So we have everything we need, we just have to plug it in. And that's going to be 3/2 times 2 moles times R, which is 8.31 joules per mole Kelvin, times a temperature of 293 Kelvin. If we do that, our answer is going to come out to about 7304 joules. So that's the total internal energy of this sample of gas. Another question we could have would be, what is the average kinetic energy per molecule? The internal energy we calculated up here is the internal energy for the entire gas sample. If you recall, to get it, the internal energy for a single molecule, it changes slightly. It becomes 3 halves times Boltzmann's constant times the temperature. And this internal energy is equal to kinetic energy. Now I just have to plug the numbers in, and my answer comes out to 6.07 times 10 to the negative 21 joules of kinetic energy per molecule. This is the kind of thing you're going to be doing using these two formula that we came up with on our first slide. Now, one thing that I think is worth mentioning is if I write the ideal gas law, PV equals nRT, I want you to notice something. nRT, nRT. Seems clear that you could actually make a substitution for nRT that would be equal to the pressure times the volume. So you could actually derive a form of this where the internal energy is 3/2 the pressure times the volume. That can and will come in handy on your worksheet. Now, of course, your pressure would have to be in Pascal and your volume would have to be in meters cubed, but that is a interesting little derivation that you can do. Good luck with your worksheets. Have at it.